Okay. Okay. I hope my screen is visible to all of you.
Yes, sir.
Okay. Uh, so welcome everyone to the ninth tutorial session of materials characterization. So as usual, we'll go through the concept and the some fundamentals that the professor has taught us throughout this week, and then we'll solve some numerical problem. Okay. So yeah, in the last class actually we left at this point that we calculated the we got to know. So first we got to know what will be the amount of intensity when the scattering happens from due to one electron. Then we calculated what will be the intensity that we'll get from an atom. That means that if there are number of n number of electrons, then what will be the intensity. And then from atom we came to the crystal structure or the lattice where many number of atoms will be there, and they will be sitting in a particular position, and how they will contribute towards the intensity, that we got to know through structure factor. And the structure, how we calculated the structure factor, the for we also calculated for BCC and FCC crystal structure. So by the summation of structure factor formula, and we got to know that in BCC only those kind of planes will come when the h plus k plus l, that means the Miller indices of a plane, when that will be equal to that will be an even number, then those planes will be reflecting in our diffraction pattern. And when h plus k plus l will not be an even number, that means an odd number, then that plane will not be appearing in reflection. Similar conditions we also derived for FCC, where HKL should be unmixed, then only the plane should be reflected in the diffraction pattern. However, if they are mixed, then the planes will not be reflected in the diffraction pattern. And finally, what we did, we calculated, we considered all the factors that might be affecting our intensity from the sample, and some of the factors will are listed it here, and this is the final expression that we got. That means I will be equal to k naught f square. So f here is the structure factor, and p we know that this is the multiplicity factor. Why we are putting this term of multiplicity factor here? Because when we are calculating the intensity, we are not discriminating between the positive planes or the negative, the positive side plane or the negative side plane. That means we are calculating we are getting that intensity from if I am talking about 111 plane, 111 family of planes, then I am getting this intensity from this family of plane of total 111. That means 1 bar 1 1 bar 1 1 in a cubic crystal structure. So all these combination, whichever is possible, so I am getting an intensity from those planes. So that is why this p value is multiplied, and this is we have termed it as the Lorentz polarization factor. Why we have incorporated it? Because our beam is unpolarized. We do not know in which direction the electric vector of this radiation is going. So that is why we have multiplied it with we wanted to incorporate a polarization term, so that our beam would be completely polarized or linearly polarized. So we have multiplied this term, and this is the e to the power minus 2m. If you remember, this is the temperature factor, that or d by Waller factor, or d by temperature factor, which we have incorporated, and 1 by 2 mu. Here this mu is the linear absorption coefficient, because when the X-ray penetrates a material, it is not necessary that all the X-rays will be reflected back. Some of the X-rays will be absorbed, and how much absorption will happen, this mu will give it to us. And this omega is the volume of the unit cell, like how much intensity we are getting from a particular area. It's not like whatever sample we are putting in the X-ray sample stage, the complete area will be giving us reflection. A certain area will be giving us reflection based on our X-ray size, X-ray beam size. Okay, so we have incorporated all this expression to get our final intensity value. But now we will go a little bit. So far whatever we have done, we have calculated this intensity considering that our sample perspective. We have not so far considered the X-ray optics side. What do you mean by X-ray optics? That means the instrumentation part of the X-ray machine, that we have so far not considered. Why the X-ray optics is necessary for us to consider? Because ultimately the X-rays are coming from the source, and after reflection or after diffraction, the rays are also getting collected by a detector. So in between those things our sample will be there. So from leaving the source to the collection by the detector, how the instrument part affects the intensity, or whether the instruments whichever we are using will affect the intensity or not, for that condition we have to see how the X-ray optics affect our intensity, because ultimately intensity is the main intensity is our main criteria. We should be getting some intensity for our material so that we will be able to index it later. Intensity versus that is the primary output of an intensity versus of an X-ray diffractogram, which gives us in y-axis it gives us intensity, in x-axis it gives us 2 theta. So intensity is one of the primary criteria or primary objective of ours. So and here optical elements in the beam part, what does it do? It tailor the characteristics of the beam. So whatever optical elements we have put in the line of the beam, that will also somehow it will affect our intensity. Okay, and that is the reason we have to see, like whether due to this optical instruments whichever we have put, whichever we are using, it will give us some variation in the intensity. And how do we see? So there are three concepts if we are going to see. One is concept of diffraction, and what does this mean? That means whether we are using a monochromator crystal or not. Okay, so diffraction means Bragg's law when we are considering n lambda is equal to 2d sin theta. So when we are considering n lambda is equal to 2d sin theta, that means here the lambda will be, it should be a monochromatic wavelength. So this value, when we are going to put this theta value here, and theta is the Bragg's angle, and d is the interplanar spacing, and n is the order of reflection. So this lambda should be a single value. That means we should be ideally getting a single value of lambda. But in the previous classes, if we remember it correctly, there will be various lambda associated with our X-ray, even with our characteristics X-ray. So one will be k alpha, another one will be k beta, and also from k alpha and k beta there will be different kind of wavelength associated with k alpha 1 and then k alpha 2. So that is why we always want to use a monochromator crystal. If we do not if we cannot use a monochromator crystal, then what will happen? Our peak will be, instead of getting a single line, we will be getting a broad line. Okay, and that will give us the peak broadening in our intensity versus 2 theta diagram. And second aspect of this X-ray optics is concept of reflection, right? So how we are going to use this reflection? So this is actually the concept of reflection, means here I have written mirrors. So remember, there is a particular type of mirror is used, that mirror is called as Gobel mirrors. So why that Gobel mirror is used, I'll tell you in a minute. So the job of this concept of reflection is to use to focus the beam, and the focusing of the beam is extremely important so that we will be getting as accurate result as possible. Okay, and the third aspect of this X-ray optics is concept of absorption. Why and which instrument we use, or which part of the instrument we use? We use the filters, we use the slits. Filters, if you remember, filters for copper K alpha radiation, what filter we are using? We are using nickel filter, right? And so that is why we are using nickel filter, because if we use nickel filter for a copper K alpha radiation, it will automatically eliminate the K beta part, right? So we will be only getting K alpha, and since we are getting K alpha, then our intensity versus 2 theta profile will be very, very good. Okay, so filter we are using, and slits. So why we are using slits? So slits, the purpose of using slits is mentioned here. You can see when the X-rays are generated, X-rays are not supposed to travel. They may or they may not travel in a exact straight line that we want. They may diverge in all directions, right? So to stop them from diverging, what we do, we put this different type of slit, or it is called as also collimators. Okay, so see here, the source, from the source the X-rays are going in all sorts of direction. However, when we put these slits kind of thing, you can consider these slits in electron microscopy. When we are studying, we are considering the aperture, right? The objective aperture, the condenser aperture. So we are stopping the unwanted electron beam in electron microscopy. So similar concept also it is used here, so that our X-ray will follow this straight path. So this is what called a collimated beam. So how we make a collimated beam, we make them using the slits. Okay, and this here, this is from source side, right? But here also we have put some solar slit, and these solar slits are also put in both source side as well as also detector side. Why? Because when after reflection, let's say my sample is here and X-ray is falling on like this, and after reflection my sample will be, I will be getting some intensity, and I might not get intensity in a particular direction. There will be always some kind of intensity I will get moving away from the Bragg's angle, and also moving that means the positive side of the Bragg angle as well as the negative side also of the Bragg angle. So that is why when I am getting this kind of peak, this kind of intensity, so my slit are also positioned in such a way that they should not be diverge more and more. My slit, what will it do? They will finally make them in a parallel position, so that my detector will be able to capture. Otherwise these diverged beams will be diverged further if I do not use this solar slit. Okay, and now coming to okay, here I want to tell you another thing, that is of Gobel mirror. I told you that concept of reflection is used for Gobel mirror. In the last class we saw that there are two circles are there. Okay, so let's say here this is source I am drawing, and here this is detector, this is the sample. Okay, and this circle is known as the goniometer circle. Okay, however, connecting the sample here, connecting the sample and source and detector, there will be another circle associated with it, and that circle is known as focusing circle. Okay, and here we can see that the focusing circle, if you connect this sample, let's say connect this sample to the circumference of the circle, you will only get one point where the perfect Bragg's reflection can take place, right? You will find one for a particular theta position. Okay, but we know that in that case, either you will get completely constructive interference, let's say I am talking about CI, or completely destructive interference, right? So either constructive interference or destructive interference. However, we know that these two are not the only phenomena that are taking place when we are getting intensity. Why? Because there is also a term called partial interference which is taking place. Okay, so that is the reason why this Gobel mirror becomes important. So considering all these three, if we want to get a perfect line condition here in this intensity versus 2 theta diagram, if we want to get a single line, then our sample should be always a curved surface, not a flat surface, right? Why this sample should be a curved surface? Because then only it will be giving us condition like even if we are deviating a little bit from in the positive side of the Bragg's angle or to the negative side towards the Bragg's angle, still we will be getting perfect, we'll be getting the diffraction condition. But we know that in real life we cannot make this the curvature in to the dimension that that is required by this focusing circle. So that is why in real life always our samples are flat, and since in our real lives our samples are flat, we are never going to get a single line when in the X-ray diffractogram. That is why we are always getting some amount of broadening due to this instrumental constraint, because we are never going to make an exact curved surface whose curvature will be matching with this circle. So that is why we keep our sample flat and then small instrumental broadening happen. And to make this phenomena work, we use this Gobel mirror. What do we use this Gobel mirror? This mirror we use so that the X-ray, the source will be little bit curved, and now that our sample we cannot make it flat, but we can make our source a little bit curved like structure. Since we can make it little bit curved, let's say from another angle, if this is now not my source, when I put a Gobel mirror, this is not my source will be somewhere here, and from here I release the X-ray beam, and based on the Gobel mirror's D, that means the interplanar spacing, this value, whichever value I will be getting, so here it will be this position, I will be getting my first reflection, right, and then this position I will be getting my second reflection, and based on this Gobel mirror's interplanar spacing I will be getting a single monochromator, because this will be this will be having only single D, and see if we are getting only single D, and if I keep the constant theta, that means my lambda will also be a single value, and since my lambda will be a single value, again I will put that lambda, that means my X-ray, into my sample, and finally I will be getting a X-ray diffractogram, right? So this is the concept of reflection, where we use the Gobel mirror. It is actually not O, it's umlaut. Okay, so it's used to focus the beam. Now coming to the monochromator, that is the concept of diffraction. The first concept we are going to see, the monochromator. So basically we use monochromator so that a particular orientation, let's say I do not want to use a variable wavelength or variable lambda, I want to use a single lambda. So what do? I use this is a single crystal. If I am talking, so this is a single crystal. Single crystal means it's having a single interplanar spacing, that means a 1D only. So so now writing n lambda is equal to 2D sin theta, right? So fixed a particular orientation, if my beam comes, right, this is the theta m. So if I am writing theta m here, my theta m is constant. Why? I am allowing my beam to fall onto the this single crystal here in a particular orientation. So theta is constant. Since I have taken this single crystal, it will be having a single D value, so my D is also constant. Now my theta is constant as well as D is also constant. That means I have also fixed my lambda now. Okay, so since I have fixed my lambda, even if I try to use a wide beam here, which will be having variable wavelength, right, which will be having variable wavelength, still when so it will be having variable wavelength, but only one wavelength out of them. Let's say it is having lambda 1 to lambda n number of wavelength, but out of all these wavelength, only one wavelength which satisfies this Bragg's condition, because my D is constant, my theta m is constant, only one wavelength will satisfy out of this, right, and that wavelength will only be reflected here. Okay, and since that wavelength will be reflected here, and using another monochromator, I can use this X-ray beam to analyze my sample towards this. Okay, and this is the use of this is actually a double beam monochromator, where the monochromator which has been used 2 times, here it is used 1 time, here it is used 2 times. Okay, and why it is used? So that I will be able to get a single wavelength, and the kind of kind of monochromator or the single crystal we use are generally silicon, germanium, quartz and diamond. So these are the examples of this thing. And what should be the characteristics of this monochromator, so that we will get a particular wavelength? So they should be good, it's good quality, first of all good quality crystal, as well as appropriate d-spacing, right? Their d-spacing should not be very too much. Their d-spacing, they should have a single d-spacing. And this is also an important criteria, mechanically strong. That means when we are cutting, they should not be breaking into several pieces. Once they break into several pieces, then what will happen? Some cracks might be generated, some residual stress might be generated when we are cutting. If it is not that much mechanically strong, then there would be variation in the D. That means their interplanar spacing, which we do not generally want. And also stable in the presence of beam. Why? Because X-ray beam or any, let's say, energetic radiation, electromagnetic radiation we are putting them under, it will be coming with huge amount of energy, and they should be able to sustain or survive that huge amount of energy. That means they should not be expand or contract more. That means they should have low CT, coefficient of thermal expansion, and they should also have low absorption. Why? Because if I am putting my beam into this single crystal and all the beam are generally, they will be absorbed inside this thing, then what I will get here? I might not get anything here, right? So they should have as low absorption as possible. And large structure factor for the chosen Bragg reflection, their mosaicity should be 0.2 to 0.5 degrees. So what do you mean by mosaicity? Mosaicity means we have considered, now if you look at this crystal, we have considered that all the planes are, let's say here, if you follow my pen marker, you can see all the crystals are oriented in a one direction, in the one particular direction. But in real life, that is never the case. In real life, all the even in a single crystal, all the planes will never be oriented in perfectly ideal manner. So there will be little bit, let's say one crystal is oriented like this, another set of, okay, like this, some kind of misalignment they might be giving. So here you can see how am I drawing. Okay, this has gone outside. So basically what I am trying to convey it here is, one, let's say instead of going in a single direction, one might be little bit down, okay, another might be little bit up, one might be little bit down, another might be a little bit up. However, since their direction is, overall direction is towards this right side, so we are considering them as a single crystal. And this misorientation that we are seeing, that is called mosaicity. And you can see the mosaicity of that thing should be 0.2 to 0.5 degree. That means if one direction would be in this direction and another would be, so the angle, this angle should be 0.2 to 0.5 degree. That means almost you can say they are oriented in a single direction. Okay, so considering all these four factors, these are the material that we use it as monochromator. Okay, and another important aspect is also of the X-ray optics is the detector. What does detector do? It captures the X-ray photons after reflection. It captures whichever has been reflected back from the sample at a Bragg's angle. It captures them and converts them to current and then to voltage. There is a system, voltage pulses, that are finally electronically counted. So that is why the I versus 2 theta in an X-ray diffractogram, if you see the there is an option of CPS. CPS means counts per second. Okay, so I is generally captured in terms of CPS, counts per second. So those are electronically counted, and this is the job of a detector. And the more, as usual in any of the instrument, the more the better will be the detector resolution, then better or the narrower peak you will get. That means good results or better results you will be able to get. And these are not actually have taught in the class, but for your information, we should know that there are three different types of mostly different. These are the three detectors which are used for in an X-ray diffractometer. One was gas proportional counter, scintillation detector, as well as silicon doped lithium detector. So they are the mechanism of those gas proportional counter is nothing. The gas proportional means it is the detector is filled with xenon gas, and when it is filled with xenon gas, and it gets ionized when the incident photon, that means the reflected photon from the this thing from the sample, when it goes and hit, let's say this is the xenon gas is here. So when this, since they are high energetic beam, these X-rays are high energetic beam, so they go and ionize the xenon gas, and then due to that, that is also connected to some circuit, and calculating its resistance, we calculate how much beam is hitting the gas proportional this counter. Okay, and similarly scintillation detector is also follows the same rule, where NaI, that means sodium iodide, is doped with thallium. When you keep this material inside this detector, then when the energy X-ray beam hits, they also emit light, and eventually those lights are counted by the photomultiplier. Here the photomultiplier, we know that it's used in also ACM detector, so same concept are also used here. And silicon doped lithium, so this is the solid state device, silicon doped lithium detector. This is the detector which is used in most of the modern X-ray diffractometer. So here we count the electron hole pairs, how many electron hole pairs are generated. So once the electron hole pairs are generated, we apply bias to the, let's say, electron is generated and hole is generated, this pair is generated, so we apply bias. That means we apply high positive voltage to this side, high negative voltage to this side. So since this is negative positive voltage, extremely high positive voltage, electrons would be coming this side, holes will be going to this side, and finally by the count of this electron we'll be able to see how much photon has hit the detector, right? So this is one of the important parameters, important aspect of our X-ray optics as well. So yes, so why I okay, we have I have written it here something, so I'll just remove it. Okay, so here, okay, that's fine. So why we are studying the X-ray optics? Because this X-ray optics eventually affect the intensity and width of the peaks, and our aim is to improve the width of the the intensity, reduce the background noise that is coming with the intensity, and to get as narrower peak as possible, right? So width of, when we are talking about the width of the diffraction peak, then naturally questions come to our mind that what factors eventually affect the width of the diffraction peak. So here, if this is a peak we are talking about, so here you can see the I peak, that means the intensity of the peak. Okay, here there is a term called full width at half maximum. We have introduced this term in the last class, that is called as FWHM. So this is one of the important term when we are doing indexing in any of our material system, FWHM. And this is the 2 theta of the 2 theta peak, and here, so this is a typical, whatever we are seeing in the right side of the slide, this is a typical peak that we get, and we know that we will not be able to get a singular line peak. Why? Because of this experimental constraint, or yes, experimental constraint, we will not be able to get a single line. Rather, we will always get some kind of peak where there would be some width will be associated with it, and some intensity at the maximum here also would be associated with it. So what factor eventually affect the width of the diffraction peak? There are 3 factors. One will be instrumental factor, that means the X-ray optics, which we said earlier, that the sample surface should be it should be having some curvature, the sample surface. Rather, we are keeping always a flat surface. Okay, that is giving some amount of broadening. Metallurgical sources, last class we have seen whether there are crystal defects are there, whether antiphase boundaries are there, whether the crystallite size or whether the strains are there, depending on the crystallite size also some amount of broadening happen. And finally the size of the sample. So these 3 things eventually will give us some, eventually will add to this peak, the peak width, right? So slowly they will, instead of getting a single line, each of these factor here, each of these factor will add slowly to the width of a diffraction peak. So we have to see what will be their effect. So now considering the instrument sources or the X-ray optics which we saw it earlier, here I have told once that to make the beam from divergent to a convergent beam or a parallel beam, we need slit. Okay, so when we need slit, that means the slit is having some amount of width, but the problem is the slit width is when you increase. Here you can see, if I go back, actually here you can see in this diagram the slit. So this one is having very small width, however this one is having very large width, right? So slit width, how does it affect our peak position and peak shape, right? So what will it do? It will not affect the peak position much, but it will affect the peak shape. How it will affect? When you increase the slit width, then the angular divergence will also be more. That means if you are allowing, let's say your X-ray is going like this, and in another case your X-rays are going like this, so whichever, so here the chances of being parallel is more than the here the in the, let's say this is the first case, this is the second case. So here the chances of being parallel in the second case is more than the chances of X-ray beam become parallel in the first case. So the more slit width you give, it will finally increase the breadth of the peak. What do you mean by the breadth of the peak? This one, it will eventually slowly it will start expanding in all this direction, towards this direction. Okay, so the more slit width will be, the more breadth of the peak you will have, and a graph has been shown here. Here the irradiation length, I will tell you what irradiation length means, but here you can see the slit width. When you are putting a slit width of 1/8, you can see the peak shape is lying here. But when you put a peak, the slit width of 2, you can see what will be the peak. That means if I want to draw something here, this complete diagram, if I want to draw, then your, let's say this is when you are opting a slit width of 2, and this is how your peak will be when you are opting a slit width of 1.8. Okay, so this is the curve. So you can see how much broadening. Eventually this broadening is coming due to instrument, right? But if we do not know about from which source this broadening is coming, what we will think? We will think that this broadening is coming due to our sample. However, and it might be the inherent properties of the sample, then all the calculation, all the knowledge about our material will be wrong. However, if we get to know what will be the instrument, what will be the broadening that is coming from the instrument, then we will be saying that, okay, I have got this amount of peak, this broadened peak I have got, but this broadening has happened due to my width. My slit width is due to I used a slit which is having more width, right? So slit width affects the instrument, the broadening of our peak. And how do we restrict them? We restrict them using the solar slit which are used at the detector. So these solar slit improve the peak shape and the resolution at low scattering angles. Particularly these solar slit are helpful so to counter the broadening effect by decreasing the width of the peak. And here is a term called irradiated volume. So why the irradiated volume is important? Irradiated volume is nothing. Let's say I have put my peak like here and my sample is here. So ideally my sample, my ray should come like this and hit my sample in this direction. But now due to this some, let's say, my divergence of my X-ray beam, so what will it happen? Some will be coming in this direction, some will be coming in this direction, and this is my sample. Okay, and now I will calculate, this one is my L1, let's say this one is my L2. Okay. So this section is my L2, this section is my L1. So if this angle is theta, then I can calculate L1 and L2. Ideally, in ideal condition, when we are talking about n lambda is equal to 2d sin theta, we are assuming that our X-ray is coming in this direction and it is being focused on a single point, right, if this beam is coming. But in reality it is focused from this point. Let's say I am changing the color. It is focusing, so we are getting information from this point till this point, right? So the combination of from this point to this point, that is called as irradiated length, and that length is given by L is equal to L1 plus L2. So how L1 plus L1 and L2 are calculated, that is out of the scope of this syllabus. But yeah, by taking simple geometry we can calculate. It's a simple sine function, so by taking geometry we can calculate. Now see, if I increase this to width of this slits, then eventually my L will also be increased, right? So my irradiated length will also increase, and according when my irradiated length will increase, then I will also get at lower angle. You can see, if my increase the slit width here at lower angle, it will be very much, it will be giving me very high broadening value for a very high slit width. So that is what I generally do not want, because we want always as narrower peak as possible, because that will give us information about our material. It will not give me information, wrong information about material, which we do not generally want. Okay, so here it is written, I have written something here. So here it is finally. So what happens, I have written it. So what happens finally is that the result, whatever we are getting, that will be a convolution or a product of the actual peak breadth function of the material, right? The final result which we will be getting, that is the result of a material, as well as some broadening coming due to the instrument. So which we do not want. We do not want a convoluted peak. So that is why we have to deconvolute the peak. Always remember, we have to deconvolute the peak. And how we will deconvolute the peak, how we will characterize our whether which shape our peak is, then we have to know about this term, that is called FWHM, which is known as full width at half maximum. We have to analyze the peak. So that is where the peak analysis is always important when we are doing the indexing of an X-ray diffractogram. So how do we analyze the shape of the peak? There are different set of functions which are associated with this this analysis. So now we know that our peaks will not be a single straight line. There will be some kind of shape, and what shape it is having. So to analyze that shape, we will be using some functions. One is Gaussian, another one is Lorentzian, another one is Pseudo-Voigt. These are the three most used function. People generally use this function, Pseudo-Voigt function. Okay, so here you don't means we don't have to use manually these things, because these things are now available in the software. So the moment you put analysis, and then it will ask you what kind of fitting you want to do, then people use mostly this Pseudo-Voigt function. There is another also good function which you can use, that is known as Pearson 7. Okay, this is also another good function which used to fit the peak shape properly. So the difference between Pseudo-Voigt, Gaussian, Lorentzian is nothing. So the Pseudo-Voigt, Gaussian, Lorentzian are two different type of function. This Pseudo-Voigt, what does it do? It takes calculation into both Lorentzian as well as Gaussian peak. So it tries to fit your peak by taking some amount of Gaussian function, by taking some amount of Lorentzian function, right? And here while fitting, you can see there is a term called WFWHM. So it is nothing but the, here if you can see here, I peak minus I background. So what is I background? If you look at this left side picture, I background is this amount of, that means intensity that you are getting. Okay, this is called I background, because here intensity, this background is coming due to diffuse scattering, or this background will come in the diffuse, these will be coming due to diffuse scattering, and they will be always associated with our peaks. So this is your I background. I peak means this will be your I peak. So FWHM means it will always be the difference between, it will be always half the difference between I peak, that means here, and I background. And this width, when we are calculating what will be the width of this FWHM, that means here, this width we are eventually calculating. Okay, so at this peak, what will be the, at this intensity, what will be the width? So this is what we calculate always, width in degree at half peak height. That means how much this difference is from here to here, how much this difference is, that will give us the FWHM in in degree, and we put that FWHM and then we try to fit whichever function we want to fit, whether it is Gaussian or whether it is Lorentzian. We will try to fit these things, right? And then so that is the analysis of the analysis of a peak. We got introduced into that. Now coming to the second factor. Remember, first factor was which contributes to the instrument the peak broadening, that was instrumental broadening or X-ray optics part, where we saw that due to here due to slit width some amount of broadening is associated. Now this slide I think we have covered it in the last class, where due to different type of cause, our broadening will be there. Low angle grain boundary, small particle size grain crystal, deformation will be there. Deformation will be there means the D value will vary, and stacking fault or antiphase boundary, compositional inhomogeneity. Due to all these factors, some amount of broadening will be associated also. And that broadening, how do we calculate? How do we know that what will be the size of our size due to those broadening? That we consider that broadening is happening due to the crystallite size. Okay, so this is called the crystallite size. It is given by, so the Shearer equation, this is the Shearer equation, where FWHM is equal to D cos theta. Many classes also, if you see, so this is written as K lambda divided by B cos theta. So here B is nothing but this FWHM, right? And this T is the crystallite size. Here I am writing T is, so D is equal to T here. Okay, so and this is the general equation. This is called the Shearer equation. This is the general equation. However, and the value of K lies from, if you remember, 0.2 to 1.2, and this K is known as a shape factor. And since we are assuming that all of our particles, or all of our crystallite, rather than I would say all of our crystallite are spherical in nature, that is why in most of the cases we have taken K value as 0.9. Okay, so this equation finally it gets converged to 0.9 lambda divided by B cos theta, right? So this is the broadening. So this FWHM, that means width of the FWHM, this broadening is coming due to crystallite, due to the size of the crystallite. Now you see, size of the crystallite is staying in the denominator term, right? That means when my size of the crystallite will be very, very small, that means in the nanometric level, you can see it will contribute to some amount of broadening. So even if I get my sample correct, even if I get my instrument ideal, even if I make my instrument ideal, there will be some amount of broadening associated with my sample. Okay, so broadening is a terminal, is a term that we can never completely eliminate from our X-ray diffractogram, right? And then this is this broadening will be coming to size effect, and the size, how do we see that how much broadening has happened? That term will be given by FWHM. Repeatedly I am telling, so that you will be this term is one of the important term, full width at half maximum. Okay, anywhere, whether you do an automatic indexing or manual indexing, so this FWHM is always important. So what does it mean? The width of the diffraction peak at a half height between background and peak maximum, whatever I have written it here. Okay, so this is what called is FWHM. And then some people have so this based on this FWHM, what we have calculated? We have calculated the Shearer's equation. However, some other scientists, okay, so found out another way of calculating or analyzing the peak, that is what known as the WIB. Instead of FWHM, they have calculated the integral breadth. Okay, so their argument was, why to only calculate this the width of the peak at exactly this height, right? Because there will be, the peak is not started here, and the peak since the peak is not started here, why we are removing the complete background? And even if we are removing the complete background, we cannot say for sure that this line and this line, they will be staying in a single this point and this point, they will be staying in a single line. Okay, there might be a peak which will be coming like this a little bit. Then in that case, which one you will consider as a background? So considering all these confusions, so what people thought that instead of putting FWHM, that means the Shearer's equation into effect, we have to, if we have to calculate the broadening due to size effect, we can calculate by determining the integral breadth. What do you mean by integral breadth? Integral breadth, so integral breadth, and so the total area under the peak divided by the peak height. This is what they have told, that integral breadth will give us correct result, correct broadening effect due to the size of the crystallite, right? So instead of using full width half maximum, we will calculate the integral breadth. And how this integral breadth is calculated? What is the significance? The width of a rectangle having the same area. That means if my peak is having this one, okay, if my peak is having this shape, then I will calculate the area. I will calculate the how I will calculate. I will take another color. So this is my peak earlier. Now I will calculate a rectangle and the area of the rectangle. So this is the length of the rectangle and this is the width of the rectangle. Let's say W I am taking, or B I am taking, the width is B. Now the area of the rectangle, let's say area of the rectangle, I will take my rectangle in such a way that area of the rectangle will be equal to area under the peak. Okay, they argued that this is the more accurate way than calculating simply full width at half maximum. So that means if there will be some rectangle whose area, okay, whose area will be equal to the area under the peak, and that the width of that rectangle I will take it as integral breadth. Okay, and however this requires a very careful attention, because little bit if you calculate little bit wrong area, then the integral breadth will be giving much larger error than full width half maximum. And here the full width half maximum has been given by Shearer, and this WIB, that means the integral breadth, is given by Lowe. You remember Lowe, who has given us that concept of diffraction first, Max von Lowe. Same Lowe, he has given us the WIB, and when he calculated that, terminology also came as lambda by d cos theta, same as Shearer's equation, but Shearer, what he has done extra, he has incorporated an additional factor called safe factor, but the function stayed more or less same. Okay, so now the size effect we have studied. Now coming to strain effect, because we cannot always say that our material is a stress-free material, because through different routes, through different process, we are producing our material. So when that thing happens, the material, if let's say no strain is there, my peak will be somewhat like this. Okay, my peak will be so this is the 2 theta if I am talking, so this is the 2 theta and this is the intensity I am talking. So my peak will be like this, and here you can see these are the different planes. Okay, and the d space and the interplanar spacing between them is d. When there is no strain, you can see my peak will be somewhat like this. But when there is modification of interplanar distance happen, that means let's say I apply some load in this direction to this crystal. Okay, so when that thing happen, what will it do? It will expand it will increase my interplanar spacing. And from this interplanar spacing, I will be getting this interplanar spacing. For now, I don't assume that, since I have written, okay, I will write differently. This is D1 and this is D2. Now, you know that D1 is less than D2. If D1 is less than D2, then what will happen? Here, n lambda is equal to 2d sine theta. So, theta will be, if d theta will be decreasing, if d2 will be increasing, then theta will be decreasing. So in this case, d is increasing, theta will be decreasing. Theta will be decreasing means now I will get the peak in this region, that means towards the left side. If I am considering that my origin, I am drawing peak in this direction, my origin is here. Okay, so my peak will be shifted towards little bit left. Now I have considered that uniform strain when it happens. That means all of my planes will be shifted in equal proportionate. But That might not be the case always. If I have a distribution of the spacing, that means non-uniform uh, strain is there, what it will do, the distance between these two planes might or might not be same always as distance between these two planes. Okay, so in that case what will happen, I will be getting, or the plane spacing varies at random, so I will be getting a more broadened kind of peak. It is means I will be getting somewhere here towards this side, but I have drawn this figure here. So you can see, let's say there are 1 2 3 4 5 6 7 8 different small peaks are there. So all due to all, that means my d spacing has 8 different d spacings are present. So if 8 different d spacing are present, so all of those d spacing will contribute towards the broadening of the peak. And finally the convolution, that means the product of all those broadening, I will get a single peak like this. That means it will broaden my peaks. So now considering size also, my crystallite size will also broaden the peak shape, and strain, if anything is there, that will also broaden my peak. Now why this uniform and non-uniform, why this broadening will happen? Because let's say this is a crystal, okay, here some rays are coming, hitting this thing, and I am getting like this in parallel manner. So it will be giving me a continuous, a line kind of structure it will be giving. However, let's say if some amount of strain is associated with it, or instead of completely these planes staying in one direction, let's say little bit misorientation has happened. First one is this, and second one is this, third one is this, let's say some kind of misorientation has happened. But in that case what will happen, since it is coming at theta b angle, some amount of reflection will go. Okay, here some amount of reflection will go. Now let's say another beam is coming and hitting at this plane, which are little bit plus or minus from the little bit deviating from the Bragg's angle. In those cases also some amount of reflection I will eventually get. Okay, and since this reflection I will be getting, so this will be giving my broadening. Instead of getting a line profile like here I was getting, this will be contribute to the broadening. And so this is a misorientation happened. Similarly, let's say defects are there and misorientation are there. Let's say this is a peak. Okay, so here let's say one particle, some defects are present, and here you can see like this. Okay, so in that case what will happen, same mixture will be coming. Let's say it is coming here and going in this direction, it is coming here and going in this direction, another ray is coming here and going in this direction. So you will be getting all this, you will be getting a completely broadened peak, right? So this is what integral breadth, or whether you talk in terms of integral breadth, that means WIB or WFWHM, width of FWHM. That is the convolution of peak broadening corresponding to size and strain. It will always be whether the crystallite size is big or crystallite size is small, or whether the strain in the material is present or it's a strain free material. So when we consider both of them, that means size effect as well as strain effect, how to calculate the FWHM or the width of the peak, that is what known as Williamson-Hall method. This is one of the most important method in total X-ray diffraction, and there is a high chance that, high probability also, that exam question might also come from this Williamson-Hall method, because it contributes both size effect as well as it comes due to size effect as well as strain effect, and the value combined strain and size contribution, and the equation is given as Fw into cos theta is equal to K into lambda size plus 4 into strain into theta, right? So here if you see Fw cos theta means, this is what we have talked about earlier, that means B cos theta. Okay, so B is here written is FW I have written so that you will understand. And when you plot this thing, you put FW cos theta as your Y, right? And sin theta, when you put it as your sin theta in terms of X, then the function has come like this is your C, and this 4 into strain will be your M. So this entire expression, right? So entire expression will be giving you Y is equal to mx plus C, where x is equal, x will be your sin theta, y will be your Fw into cos theta, and m will be your 4 into strain, x and C will be your k into lambda by psi. And the graph will be like this here. Okay, next so the graph will be like this. You have to yeah, if you can see any book, the derivation is there, but if you don't want to go much deeper into the derivation, you have to remember this formula: Fw into cos theta is equal to k lambda divided by psi plus 4 strain sin theta. Why it is important? Because so this is your y axis, this is your x axis. So now we can say that k into lambda into psi, that means if this kind of, why this I told that this might come in the examination, because asking by giving a single graph, a question, an examiner can ask many questions. So if they give this thing, then they might ask you what is the size of the crystal. Then what do you have to do? You know that C means the intercept, y is equal to mx plus C. So m is here the slope, C is here the intercept. So if someone gives you this kind of graph and say what is the intercept, then you will be knowing that this is my intercept. What is the slope? You know that this is sin theta, so you have to measure the slope. This is y, this is x. So by measuring the slope, you can calculate here, sorry, delta y, delta x. By measuring this thing, you will be able to calculate slope. And what will be the slope? Slope value is 4 into strain. That means you will be easily able to calculate the strain associated with the sample. Okay, so that is why this equation is one of the most important equation in X-ray diffraction. So it combines the strain as well as size contribution to the broadening effect. However, now if you see that if the broadening comes only due to the size, not due to the strain, then what will be this curve will be looking like, right? So let's say this is sin theta, this is y, I am writing it here y, that means Fw cos theta. Okay, if the broadening will be coming only due to the size effect, size means this terminology, only C, that means there will be some amount of C associated with it, and there will be no slope. No slope means zero slope. So what do you mean by zero slope? The whichever broadening it will be coming, the FWHM value you will be getting, it will be coming in a horizontal manner parallel to your x-axis, right? And similarly, let's say no size, only strain will be there. Okay, when only strain will be there, no size effect, for now we are ignoring size effect. When that thing happens, what will be 4 sin theta, Fw cos theta will be 4 sin theta. In that case, if we are considering this terminology as 0, let's say C we are putting as 0, how the equation will go? I'll draw it with another color. So the equation will go like this, right? The equation will be somehow linear to, that means y is equal to mx. Simply this equation will be giving y is equal to mx. Why? Because there will be no C. What does C indicate? C indicates the size effect, right? So since combining these two, y is equal to mx and y is equal to here C, we are getting finally a curve like this. I will be putting it in another color. So we are finally getting a curve like this. So this, sorry, just yeah. So finally we will be getting a curve like this, which incorporates y is equal to mx plus C. Okay, so this is one of the most important equation. Again I say that Fw cos theta is equal to k alpha, and alpha we know already. This alpha belongs to the wavelength of our radiation, and it will be given all the time. What is the value of alpha? You don't have to worry about that. And then finally we can calculate strain, we can calculate size also, right? So now coming to the but now knowing that how we can analyze the thing, how we can analyze a peak, what are the important parameters that we should know, and how we have to know all these things. So ultimately all those information we will get when we identify our sample, right? So if we are not able to identify our sample, then we will not be able to get all the information. We cannot index those things, and once we cannot index those things, then we will not be able to get further information. So now comes the important section of the X-ray diffraction, that is the identification of an unknown sample. That means whatever the measured data we are getting it here, the measured data, it is the comparison of the measured data with the database, with a certain database, by use of computer search. Why computer search? We will see it when we are doing the indexing. So using the computer search, and how those databases are generated, those databases are generated by using different standards. Generally the standards are some standards are used. One standard uses Y2O3 standard, another one is, so this graphite monochromator and Y2O3 monochromator. So these kind of monochromators are used for generating the standard data. Okay, and there should be a body who should regulate this who should take care of this database. So that body is known as Joint Committee on Powder Diffraction Standard, or as famously known, JCPDS. So all the research paper that we are reading, there will be a JCPDS file number. We will always be giving the JCPDS file number is, let's say 00071 something, then we give some number, right? 00110716, or this kind of numbers we always give. So that is nothing but this JCPDS file, and this is the committee which decide which standard are to be kept where. And from 1978 this has been renamed as International Center for Diffraction Data. Okay, and this is known as ICDD. So whenever we are searching, we are doing an analysis, we always say that ICDD database we have to match it with. Our data should be matched with ICDD database. That is what this International Center for Diffraction Data. And how do we? So now knowing all about a little bit this about the standard bodies, who regulates this database. So we'll go a little bit into how to calculate how to identify actually the unwanted unknown sample. So there are two methods associated with it. One is Hannah-Welt method, another one is Fink's method. So what does Hannah-Welt's method say? Hannah-Welt's method, it tells us that you use three most intense peak. You use three, that means you index three most intense peak and calculate their D1, D2 and D3 where they are situated, and accordingly you calculate the HKL value. Indexing means there will be this kind of structure we will be getting. We will be giving each, and we will be naming them according to their Miller indices, which HKL value these peaks correspond to. That's what indexing means. So to do an indexing, if we are following the Hannah-Welt method, we have to take three most intense peak, then calculate their D1, D2, D3 and accordingly calculate their HKL value. However, the Hannah-Welt method, the problem is, if let's say there is a texture in the sample, since it is saying that the three most intense peak, there is a texture in the sample, or there are not sufficient amount of intense peak in the sample due to the size of the sample is very low. So in that case, Hannah-Welt's method might give us some wrong result. So that is why another method has been chosen, that is called as Fink's method or Fink's indexing. So here what do we do? We take 8 most intense peak, and generally in 8 most intense peak are sufficient. Even if there is a texture, it might not be propagated to all the peaks. So even if there is there has been a peak shift between 2-3 peaks, rest 5 peaks will give us somewhat accurate results. Okay, so this so here you have to index 8 most intense peak. However, in Hannah-Welt method you have to index 3 most intense peak. Now we do the computer search by putting our material X-ray diffractogram in a particular software. There are different types of software associated with it. We will not go detail into that. Let's say I'm using a particular software. Now I matched my data, my measured data has matched with a standard data here. Then then there will be many standard data which will be matching with my measured data. Then how do I determine what is the quality of data that I want? Then there are different types of quality of data which I want. One will be star, indexed, low precision, blank, Rietveld, and hypothetical. These are the most qualitative data that we want our sample to match with this data. What do we mean by star? This is the best quality data. Okay, best quality data means whichever peaks you are getting in your X-ray diffractogram, all the peaks intensity as well as all the peak position are matching with this file, with the standard data. That means all peaks in a star file, all peaks are indexed. Not a single peak is remaining. In a star file, all peaks are indexed. Then comes indexed quality. Okay, so when you are going to go to indexed quality, it is a little bit lesser than the star quality, but there will be two unindexed peak. At least, not at least, two unindexed peak. If your data is matching with a standard data with quality index, that means in the standard data base itself there will be two unindexed peak. Rest of them, let's say you have got 16 number of peaks. Generally it doesn't come like that, but let's for now assume that 16 number of peaks you have got between 10 to 90 degree 2 theta position. Okay, so out of those things you have not been able to match the two unindexed peaks because this quality is indexed. Similarly, low precision means it is at least 3 unindexed peaks. At least I am talking here. Here I am telling in the standard file with which your measured data is matching, that standard file itself does not have at least 3 unindexed peak. It might have more than 3 unindexed peak. That means the standard file itself has not been completely indexed, right? And blank means no indexed peak. Okay, no indexed peak. Generally we stay star, indexed, and there is also another one I have forgot. So that is what called as calculated. Okay, so calculated is also another quality data. Generally we stay in star, indexed, or calculated. These are the 3 qualitative data that we want our sample to our measured data to match with it. Rietveld means the amount of so we do Rietveld refinement to match our data with any of the other by taking all the theoretical values, their atomic position. So we calculate, we do the refinement, and this is the Rietveld quality. And then hypothetical is we theoretically calculate by taking the temperature factor, by taking the absorption factor, we calculate and we see what is the quality of the data that we are getting. Okay, so this is what so here you might have heard about the Rietveld refinement. Okay, so it will give us exact data for our own sample. Okay, it will not give us exact data for the standard sample, but for our own sample, whether it is having a single phase, whether the if it is a mixture of a phase is there, then which phase, what will be the amount of phase that is present in a particular mixture. All these things we will get to know from Rietveld refinement. What will be the accurate crystallite size, what is the density of defects present in our data. So all those information will be able to get from Rietveld refinement. Generally star, indexed, calculated, these 3 quality of star data matching with a star data is very rare. We sometimes if we do a very good experiment, a clean experiment, we will get the star data. Otherwise indexed as well as calculated are also equally fine. Okay, so this is the quality of data. So always check for the quality of data in database before indexing. Okay, this is this thing. And then comes the quantitative analysis of powder mixture. So far we have considered that our material is pure, so there is no phase in the material. But let's say our material is having some other phases also along with the primary phase. So what will you do? So there are many methods are there. One is so out of which I have mentioned it here, two method. One is direct comparison method, another one is internal standard method. Also there is another method that is called external standard method. There is another method is also called as RIR method. Okay, so as you study, there will be many methods for calculation of quantitative analysis. However, the direct comparison method and the internal standard method are the one which we will study, we will see. Okay, so what do you mean by the direct comparison method? Here I am again mentioning this integrated intensity expression. Here we can see I is equal to k naught f square. So this multiplicity factor, structure factor, by taking everything into account, I have mentioned this thing. Now I can write this thing in terms of, I do not want to, I know the structure factor for a crystal system is constant, P is constant. If I am saying that my theta will be, if I know the theta value, then this thing will also be constant. So instead of writing it in this term, what I will do, I will put like k naught. If I put this entire term, okay, if I put this entire term as R, so I can write now, I'll change the color, writing it in violet. So I can write now k naught R divided by 2 mu, right? I can write this entire expression in terms of k naught into R divided by 2 mu. Why it is important for me, why I have written it like this? Because ultimately this k naught is a constant. That means Thomson scattering, it is considering cross sectional area of the X-ray beam. It doesn't have to do with this term, anything with the angular variation that my so I am getting my information from. So now if I have to consider, let's say I am considering a binary system which is having alpha and beta, then the intensity of a diffraction P corresponding to the alpha will be, if I am considering that term as I alpha, then it will be C alpha K1 by mu naught. Here remember I have written K1. So this K1 is nothing but the factor here, this K naught. Okay, why I have written K1? Because this K naught and K1 might not be same, but it is also another. Here for your clarification I am writing here, it is another constant terminology. Okay, so when I am talking in terms of this one, what is this C alpha now? The C alpha is the volume fraction of alpha in the mixture. Here I am writing, this is the volume fraction of alpha. That means this I alpha intensity whichever I am getting now, it is only coming due to alpha amount of phase. It is not corresponding, it is not coming due to beta phase which is present in the system. So how I will calculate the volume fraction of alpha in the system? W alpha rho alpha into rho m. You don't have to see this derivation. I'm just mentioning it here so that you know how these things are calculated. Then in that
they're practicing for class.
So you will see how these things are. You should know how these things are calculated, and then now that I know alpha and beta both are present, then the intensity of diffraction P corresponding to alpha will be different, intensity of the diffraction P corresponding to beta will be different, right? So if I put all those two things into my expression, then I will get I alpha is equal to K, I am mentioning the constant is K naught dash, okay, and here I beta will be something, this thing. That means these two terms, if you see from here, K naught and 2 mu, they did not change, okay, because those things are associated with the bulk amount of with the total sample. And here this R alpha C alpha, I am putting it here, these are associated with the fractional phase that is present in my sample. So that is why the R has converted into two things, one is R alpha and another one is converted into R beta. Now how much R alpha is contributing? It is contributing according to its volume fraction in the present in the material. How much R beta is contributing? R beta is contributing according to its volume fraction present in the material. So now if I take I alpha and I beta, these terminologies are coming. Now if I divide I alpha by I beta, then K naught will be cancelled, 2 mu m, that means mu of mixture, mu m means mu of mixture, linear absorption coefficient of the mixture. So those will be gone, you will be coming with this expression. and in this expression you are getting I alpha by I beta is equal to R alpha C alpha divided by R beta C beta. It's a simple expression. However, you should know which terminology you will be able to get from which thing. This I alpha I beta you will be getting from your indexed from your X-ray diffractogram. Okay, ratio measured from the diffraction experiment. How you will get, you will be able to know which one which I alpha, which one will be I beta? By indexing. Let's say after you do the indexing, you will get to know that there are 4 peaks are there. Okay, this is I, this is 2 theta. So you know that this phase belongs to alpha, this phase belongs to alpha, this is beta, this is alpha. You will be able to know which phase belongs to which one. Then you have to decide I alpha by I beta by taking their most intense peak. Okay, so from this experiment, this I alpha by I beta you will be getting to know from the diffraction experiment. Then R alpha by R beta you have to calculate theoretically. Why? Because Lorentz polarization factor, temperature factor, Debye-Waller factor, or multiplicity factor and structure factor, you have to calculate it by yourself by knowing your material's history. What material it might be, what crystal structure it might be. By knowing your material's history, you have to calculate this term. Then you will be finally getting a term in terms of C alpha by C beta of some function. Okay, now that you know C alpha by C beta, also you know that there are two, this is a binary system, right, all consisting of alpha beta, and volume fraction of alpha is C alpha, volume fraction of beta is C beta. So if you add them, C alpha by C beta, then you will be getting total volume fraction. This is equation number 1, this is equation number 2. So solve these two equations, you will be getting C alpha, you will be getting C beta. That is how you calculate the volume fraction of alpha and beta, or let's say any for that matter any phases in the in your mixture, in your system. So this is what direct comparison method is all about. Now coming to the final part of this X-ray diffractogram, X-ray diffraction is the indexing of peaks. So far we have all talked about that we have to index the peak, we have to index the there will be different peaks according to different 2 theta value, position value will be different. So how do we index a peak? By taking a simple cubic system, means we will see how we will index the peak. So the main fundamental or the main mechanism that is used for indexing is this thing, Bragg's law combined with interplanar spacing of any system, that is how we index the peak. And how do we index the peak? Here means I have written this expression, okay, and just okay. So here how do we come to this equation? We know that n lambda is equal to 2d sine theta, right? And let's say I am considering now first order reflection, then lambda is equal to 2d sine theta, and that means d will be is equal to how much? D will be equal to lambda by 2 sine theta, and we know that d value will be how much? So here if we put the d value, okay, I'll write it by squaring this thing, by squaring the expression of this expression, we will be getting d square is equal to lambda square by 4 sine square theta, right? Lambda square by 4 sine square theta. And now if you put the d value will be what is the d value? 1 by d square is equal to h square plus k square plus l square by a square. So this is the d value, right? And d square will be equal to a square divided by h square plus k square plus l square is equal to lambda square by 4 sine square theta. So from this equation, when you do an arrangement like this, when you rearrange all this thing, you will get an equation like sine square divided by h square plus k square plus l square is equal to lambda square by 4a. Okay, so this is what you will get. Now I know that in a cubic system, h square plus k square plus l square will be always an integer, and since I know
the lattice parameter for a cubic system, it will be always constant. Why? Because I am considering a crystalline material and there will be periodicity in our material, right? And since the periodicity will be there, the lattice parameter will be constant in a cubic system. So now this is constant, lambda is also constant. That means this entire thing is also constant. So if we follow, we will be able to follow this expression while doing the manual indexing of our peak. By while calculating the D value as well as the A value, we will be able to get HKL. So this is what called as indexing of a peak. For that, to know those things, we will take an example here. How we will know that the indexing, whatever we have done, is correct or not? This is a simple trick that we generally follow, that if the system is simple cubic, so indexing is nothing but assigning HKL value to your peaks, to your X-ray diffractogram, the peaks in the X-ray diffractogram. So how will you assign all the HKL value? So generally we see that if it is a simple cubic, look at here, then all the simple cubic means all the reflections will be present. How we know that all the reflections will be present? From the structure factor calculation. So this is where the structure factor calculation comes into play. So since all the reflection will be present, so that means 100 will be there, 110 will be there, 111 will be there, like here you can see it in this thing. Now coming to the body centered or BCC structure. So BCC structure means you will always get the combination should be, the H plus K plus L should be 2n, right? So you will get all the peaks or all the planes in such a manner where you will, if I say 100, let's say, let's take this plane 100, H plus K plus L is equal to 1, which is an even number. That means this peak will be absent in BCC structure. Okay, so that is why the first peak that we will get in the BCC structure 110. Here you will get 110. The next structure 111, it will 111, if you see it here 111, this is coming in simple cubic, but it is absent. Why? Because 111, that means 1 plus 1 plus 1, 3 is an odd number. It is not going to be present in a BCC system because its structure factor is 0 and its reflection will not come. Then the next peak is 200. That peak, will it come or not? 2 plus 0 plus 0, it is 2. 2 means it is an even number. Even number means it will be present. So this is how you will calculate. We will see how the BCC will be coming. And whether I have written. So there is also another thing that we see. Here I have told you that h square plus k square plus l square will be an integer. And looking at all this structure factor calculation, we generally have a rule h square plus k square plus l square. For simple cubic, this value can take 1, 2, 3, 4, 5, all these values it can take. For BCC, this h square plus k square plus l square will be coming 2, 4, 6, 8 in this manner. For FCC, whatever HKL value will be coming, it will be coming in terms of 3, 4, 8, 11, 12 in this manner. Okay, same for diamond also, same for this hexagonal also. We do this, all these things. Now if you see, there is a catch here. If you see how, by looking at it X-ray diffractogram, if you know that your sample is cubic, by looking at an X-ray diffractogram, how you can say that this is BCC or FCC, we'll see it in a problem by solving one problem here. Let's say this will be the data indexing problem. If it comes in your examination, like this table will be only here this is the first table, let's say this is the second table, the first table will only be given to you. Okay, now how to come from first table to the second table? Okay, so this is, you have to, so first table will be given, second table will be the answer. So how you can come from first table to second table, I will show you, and that is what known as indexing of a X-ray diffractogram. So here you can see the 2 theta is given, right, and only D value is given, right. So now coming to, so since 2 theta value is given, you can do another table from 2 theta. Let's say I am putting another column here. From 2 theta we can calculate theta here. right? So we can calculate theta. Now that we know the theta value, we can calculate sine theta value for each and every angle. This angle, we can calculate sine theta value. Now that we know that sine theta value we have calculated, we can calculate 4 sine square theta by lambda square. Why I have taken this term? You have to remember this formula, sine square theta, this formula, sine square theta by, so sine square theta by h square plus k square plus l square is equal to lambda square. I am writing it here. So sine square theta by h square plus k square plus l square is equal to lambda square by 4a square, right? If I take this 4 to here, that means 4 sine square theta divided by h square plus k square plus l square is equal to lambda square by a square. I know that my lattice parameter is constant, lambda square is constant because I have a fixed wavelength. So this value will also be a constant value. So that is why I calculated 4 square lambda. Okay. So instead, here h square plus k square plus l square value I have to calculate. So I will take this thing there and lambda I will take it here. So I will calculate 4 sine square theta by lambda square because this lambda square is known to me. So when I calculate this terminology, I will finally get h square plus k square plus l square by a square, right? I will get this term. Now I have got in terms of this thing 24, 48, 72, 96. Now you have to assume something or you have to do a trial and error method. Now you can see that if you are getting 24, 48, 72 and 96, that means what you do, you divide this each and every terminology with the minimum value that you have got it here, right? Let's say the minimum value, what is the minimum value? 24.0113. Okay, so when 24.0113, you are dividing 24.0113 divided by what is the minimum value? 24.0113, right? So it will give you 1. Next, you divide this one, 48 point this value. When you divide, it will be coming some close to 2, then 3, then 4. You will get this kind of expression. So S you will be getting this h square plus k square plus l square you will be getting, right? Accordingly you can write this is 1, 2, 3, 4. Which crystal structure it might come? It might come as an SCC, that means simple cubic crystal structure. But you should not be you should not stop there, because the moment you stop there, then that will be a problem. Why? You have to calculate A. Once you see that this is 1, this is 2, this is 3, this is 4, and accordingly you assign h1 this HKL value. 1 means you will be assigning 100, 2 means you will be assigning 110, right? So accordingly this HKL value if you assign, then A value will not remain constant. Remember, A value has to be constant. Okay, so that is why, again, now that you know your A value is not constant, what you have to do? You have to do again indexing. So what you will do? You have to look at the next thing, that you have to, you see this is 1, 2, 3, 4, then you have to multiply all these 1, 2, 3, 4 with the next integer, so that you will get this kind of values. So if which thing, if I have to multiply with S simple cubic, it will get BCC. If I multiply this 1, 2, 3, 4, if I multiply 2 with them, then I will be getting the value of 2. 2 into 2, 4, 6, 8, right? I will be getting this value 2468, which I have got it here. Okay. Now according to 2468, when I assign my HKL value 110, 200, 211, 220, I got my HKL value, and after getting the HKL value, when I calculated my A, then you can see the A values are almost constant. That means the simple cubic which you are earlier getting from this table, it is not the correct one. The B2468, that means whichever reflection you are getting reflection from a BCC crystal structure. Okay, so this is how you do all this indexing. And the catch to calculate the BCC and to catch to see the interesting part to see the BCC crystal structure is all the peaks will be appearing at equal intervals. So that means if you are getting a peak like this in equal interval, if you are getting, then that is a most likely that is a BCC material. So by looking at a normal diffraction peak, you will be able to see what is the difference between BCC, what is the difference between FCC. Now coming to another problem, we will try to solve same thing here. So this kind of in this kind of question might come in examination. Only 2 theta, I have taken this thing from a book. So only 2 theta values will be given to you, nothing else. So from 2 theta, how will you let's say the material has been given, how will you calculate the value of, how will you index each of these peaks? 1, 2, 3, 4, 5, 6, 7, 8 peaks are there. How will you able to index those 8 peaks? So same thing, I have done it for two angular position. You can subsequently do. How? So what you will do? 2 theta. 2 theta means after 2 theta, what will you do? Always make a table writing everything 2 theta. After 2 theta, you will be doing a theta calculation, and from theta you will be doing sine theta, and from them sine square theta. Now same thing you do sine square theta by sine square theta minimum. So when you do all this thing, okay, when you divide this thing in, you will be getting expression like 1. You will be getting expression like 1.33. But you know that 1.33, and then subsequently you will be getting some other term. Those are not the reflection here. These are not the terminology. 1.33, it is not a value that h square plus k square plus l square will have. So that is why you have to you have to pay a little attention, so that you multiply this terminology with such a term, with such an integer, that finally you will be able to get an integer value, not an decimal value. So what value I have to multiply? I can do, so see, here I have directly multiplied 3, but I could have multiplied 1, I could have multiplied 2, right? So when I multiply 1 with, that means the entire column should be multiplied with 1. When I have to multiply 2, the entire column has to be multiplied with 2. Then only you will be able to get. So when I multiplied 1 with 1, I will be getting 1. Okay, 1 means the first reflection of the simple cubic is 1. Then when I multiply 1 with this terminology, 1.33, I am not getting. That means 1 is out of the syllabus. Now let's start with the 2 value here. Okay, so when I multiply 2 with this column, so if I multiply 2 here, I will be getting 2. Okay, so I will be getting in this column, I will be getting 2. When I multiply 2 here, 1.33, I will be getting 2.66. Will 2.66 was 2.66 present here in this h plus k square plus l square value? No. So that is why 2 is also not an option. Then I will be coming to 3. When I multiply 3, okay, then what will happen? 1 into 3, I am getting an integer. 1.33 into 3, I am getting 3.999. That means it is close to 4. If I put an integer, if I round them up, it will be close to 4. So I have got my first S value as 3, second S value as 4. That means subsequently, let's say if you do all these things, it will come it as an FCC crystal. And how to know, without even knowing how to know that this is an FCC crystal? FCC crystal, the X-ray diffractogram of FCC crystal, remember they will always come in 2-1-2-1 pair. Here you can see these 2 peaks are almost together. Then this 1 peak is there. Then this peak is, these 2 peaks are together. The distance between 2 peaks is not same the distance between these 2 peaks. So these 2 are together. Then again one small peak is there. These 2 peaks are together. Okay, so in 2-1-2-1-2, in this manner the peaks will be coming. So that is what here also, if you can notice, 3-4 they are together, 8 is alone, 11-12 they are together, then the next term will be alone. So that is how you have to see that whether this peak which is coming, it is an FCC, BCC or any other crystal system. This is also another thing you have I have taken from previous year lectures. So here you can see, after indexing, After indexing, once you get to know this S value, that means 3, 4, 8, 11, 12, 16, 19, you will easily know that this is an FCC crystal structure. How they have done? Theta, from theta sine square theta, then sine square theta they have multiplied with sine square theta, and then putting lambda square by 4a square, they finally, and you can see here they have calculated the A should be constant irrespective of let's say you are not getting anything, any FCC, whether it's FCC or BCC, you have indexed something, you should always calculate A, because this will ultimately give you the indexing that you have done, whether it's correct or wrong. Okay, so yes, that concludes our session for today. Now let's go through the problems. So this is our first problem. So the problem states that what acceleration potential V must be applied to electrons to cause electron diffraction on 2 to 0 planes of gold AU at theta equal to 5 degree. So atomic volume V molar has been given. So yeah, so we'll do this problem. So you can take 1 minute of time and then we'll solve this thing. Has anyone solved this problem? Has anyone seen anywhere? You can let me know directly. Okay, so we'll solve this problem now. Was anyone able to do it? Okay, is there any answer in the group? No. Okay, so okay, we'll see how is it done. So it has asked about acceleration potential V, and what are the given that has been there? 2 to 0 planes, that means the HKL value is given. HKL value is given. Gold it has mentioned, and yeah, the crystal structure of gold, if you remember anyone, FCC, that means it's a cubic structure, and theta is given. So it has asked what acceleration potential to cause diffraction. So we know that it is somehow relating diffraction, that means the wavelength with the acceleration potential. So here I am writing some we have gone through those equations. So we know that the de Broglie's relations. What is the de Broglie's relations? It is given by lambda is equal to h by momentum. Momentum, let's say I am talking in terms of P, then momentum is mass into velocity, small v I am talking it here, right? And this mv, when I am saying that half mv square, that means kinetic energy, will be equal to potential energy when a charged particle goes in a potential of acceleration potential of v. So this will be the potential energy, this will be the kinetic energy. When we put this thing, then mv will be, so we have to combine these two together, right? And then this will be, v will be, small v will be 2 ev capital V divided by m, right? So by putting this terminology here, we will be getting 2me capital V underscore. So now we know that from de Broglie's relation, lambda is equal to, here I am writing it again, lambda is equal to h. H is the Planck's constant, whose value is 6.626 into 10 to the power minus 34 joule into second. So 2mev capital V it is. So this is my equation. So this equation relates the V, which is acceleration potential, with the lambda. Now the question for me, I have to calculate, let's say I'll change the color, I have to calculate this term. I know E. What is E? E is the charge of electron, 1.6 into 10 to the power minus 19. What is M? M is the mass of the
electron, because here electron diffraction I am talking about, which is 9.1 into 10 to the power minus 31 kg. 2, I know h, I know Planck's constant. That means for me to calculate V, I have to know lambda first. Lambda means wavelength. And how I will know lambda? When I know lambda is equal to 2dHkL sine theta, right? So in this equation, if I find lambda, then I will be able to put this lambda here and I will be able to calculate h by 2 MeV. Okay, so how I will calculate whether, now I have to see in this equation whether all the parameters are there. So theta is given directly 5 degree. Okay, now DHKL it is not given. So how do I calculate DHKL? I have told here this is a cold material, that means FCC. So I have to put the equation for getting D. 1 by D square is equal to H square plus K square plus L square divided by A square. Now I will see whether all these expressions, all these equations are given me. H square plus K square plus L square I can find out because I know HKL 220, right? But how do I know A square? A square is not there. A square is, A means the lattice parameter. So how will I calculate A here so that I will put it, right? So here another terminology is given as V molar, that means molar volume has been given, per mole it has been given. So how do I calculate molar volume? So molar volume is given by, let's say, AQ lattice parameter per mole, that means Avogadro's number, right? This is Avogadro's number into the lattice parameter divided by, I will do a 4. Why this 4 terminology, the 4 value is coming? That means whatever the molar volume I am getting due to the number, since in FCC there are 4 atoms are present in a lattice. So that is why the molar volume which will be contributed is big, will be contributed due to 4 atoms. But I need only the molar volume of 1 atom. So that is why I will divide this 4. So now from here I will see whether all these things are given or not. So when I see, then let's say now A will be, I am writing 4 into V molar divided by Na, that means Avogadro's number square root of 3. Okay, so now I can see that all these expressions are currently given to me. 4 I know, V molar A is given 10.2, Na 6.023 into 10 to the power 23. Now I will get some value of A. A will be coming, I don't know, yeah, A will be coming somewhere close to 4 point something, if I remember correctly, 4.07 angstrom or something. A value will be coming. Now put this A value here, you will be getting D value, right? Now put this D value here, you will be getting lambda value. Now put this lambda value here, you will be getting the acceleration potential. Okay, so acceleration potential will be I don't know how much it will be, close to, if you are doing calculation with me, it will be close to 2400 something, 2415 volt or something. That was the answer. I'll just check it. If anyone has calculated, can you confirm what is the acceleration potential? I have calculated somewhere. It is no, this is not 2. The value is coming close to 2415. That is the value. Yes, this is the value, 2415. Okay, so this might be a long question answer which will be coming in your examination, because you have to calculate, you have to actually calculate 1 2 3 equations you have to put, then you have to calculate the answer. Okay, so similar to this question, now we will be going to the next question, that is, what is the maximum wavelength of radiation capable of second order diffraction in platinum? Here platinum is, again I am telling, FCC, V molar has been given, second order diffraction.
Okay, that means n value is equal to, we always take n value is 1. Now it has exclusively asked us to take n value as 2. So what is the maximum wavelength? So we will write n lambda is equal to 2d sine theta. So when maximum wavelength will come, this entire value should be maximum. This entire value should be maximum means what? D value should be maximum. This value should be also maximum. And when sine theta value will be maximum? The maximum value of sine theta is 1. When theta will be equal to 90 degree, right? So now considering this equation, when I am writing n lambda is equal to 2d sine theta, 2 lambda is equal to 2d, always start writing or practice writing d HKL, okay, so that you will not forget which index or which plane you are writing. So d HKL sine theta value, this will be 1. So 2 cancelled, so lambda is equal to d HKL, right? So it has asked us what is the value of lambda. That means we have to calculate ultimately what will be the value of d. So how will you calculate the value of d? I'll take another color, let's say this one. The value of d will be 1 by d square is equal to h square plus k square plus l square divided by a square, since it is cubic structure, right? So this is the value, and here what are the value that has been given? H square. Okay, so from here you have to calculate the a value. So how do you calculate the a value? Let's say I am taking another one. So a value we can calculate by putting 4 into molar volume. Remember, this molar volume, it has been given in centimeter cube. You have to convert it into standard SI unit, that is meter cube. So that means here there will be a 10 to the power minus 6 term will be associated. You have to always, when you are doing any calculation, if it is not mentioned, then you have to do it in SI unit. Okay, so molar volume divided by Na. So from here you will get the A value, and so for you to get the maximum D value, this H square plus K square, if you reverse this equation, I am writing it here. So D square is equal to A square plus H square plus K square plus L square, right? So for you to get a maximum D value, you have to get maximum A value, but A value is constant. That means you have to get minimum H square plus K square plus L square. For an FCC, what is the first what is the least value of H square plus K square plus L square? We have seen it here. Where? This is here. That means the H plus K plus L will be equal to 3. H square plus L square plus L square. It will be equal to 3. This value you put it here, A value you put, D value you got it. Now D value will be equal to your lambda. So the correct answer will be, you will be getting answers. So I will just write it here. Answers will be, yeah, the lambda value 2.26 angstrom. If you are getting any close to this value, then it's correct. Okay. I did not give this options here because you will be getting angstrom value. So yeah. So this is another type of question. This can also come as a long question, long answer question. Now these are the numericals. Okay, yeah, this is a conceptual question. If any one of you knows, just tell me. So what is the crystal structure of magnesium, KBr, alpha iron, silicon and lead in order? Does any one of you know what will be the answer? Okay, so the answer will be alpha iron. Alpha iron, we know that it is BCC, and then what? Silicon. These are the important some things you have to little bit remember, so that even if they instead of sometimes they are asking the structure factor of that particular crystal system, they might ask some of the materials as well. So lead is also Cc. Magnesium, however, it's HCP. So HCP, FCC, I think C. KBr, it is a FCC. So C is the answer, FCP. Okay, so you have to remember not much. Another one you have to remember, aluminium, Au. Okay, here it is alpha iron. There is also gamma iron, that is FCC. So some of the important aluminium, iron, Ag, you have to remember, platinum. So these are nickel. Yeah, these are the almost set of the material which they will ask, and based on that they might ask you to derive the structure factor. And some of the compounds also, super alloys, they might ask Ni3Al. That is another important aspect. This is the super alloy which is used in gas turbine engine in aeroplane. Okay, so these are the set of materials they might ask you for the derivation of structure factor. Okay, so next question is, the intensity of the X-ray diffraction peak of a particular phase is dashed to the concentration of that phase, directly proportional or indirectly proportional? So can anyone answer? We have seen the direct the comparison.
Yes, sir.
Which one?
Yes, sir. Indirectly proportional.
No, it is related to the direct comparison method, right? Concentration of that phase, how much volume fraction will be present there, so that will dictate the concentration, right? So the correct answer is B. Remember, I told you the equation related to this is I alpha by I beta. Okay, R alpha into C alpha divided by R beta into C beta. So here C alpha by C beta is the volume fraction. So this will be eventually, if you convert to concentration, so same relation will also hold. So that means they're directly proportional. The more amount of material or the more concentrated material are present, if they are present in your system, then the intensity of the peak will be higher. That is the physical significance of this equation. Okay, and yes, okay, so this is a terminology, this is a question associated with the Rietveld method, though we have not studied, but yeah, I have told some of the lines also in the lecture. Can any one of you answer statement, which statement are the correct? So refine information about a single crystal structure, refine information about a single sample, refine information about a multi-phase sample. So which one is correct? It is asking. Any one of you can answer? Rietveld method gives, okay, someone has written something, C. Yeah, that is the correct answer. So it gives us information about a single crystal structure. It gives single sample, whether it is what are the phases that are present in the same sample, what is the FWHM, what is the crystallite size, and it also gives us information about a multi-phase sample. Why it has written refine information? Because all this information we can get from normal indexing as well, but it will not be as accurate as a Rietveld method, because normal indexing, when we do, we put as we put some kind of function, but we do the analysis, we do the fitting a number of times, like 1, 2, 3 times we do the fitting, peak fitting, when we do the indexing. But when we are talking about the Rietveld refinement, until and unless the value, there is a value of R square, so that value should lie between 0 to 1. Okay, so until and unless that value, you are bringing this value, R square value, between 0 to 1, that is the goodness of the fit it will represent, you will not be, so you have to do multiple Rietveld refinement. So that is why it refines each and every parameter. It's slowly it refines. It takes consideration into all the UVW term. It takes consideration of all the ABC terms, that means lattice parameter, all the your X-ray your machine parameters, that means instrument broadening. All these things it will refine one by one, and then it will fit to your equation. So that is why it is a refinement. Rietveld is a refinement method, so we do it for for the accurate measurement of our sample. So option will be C. Okay, so the next question is related to the previous question. The examination of X-ray diffraction. What is the time now? 8:01. Okay, we'll be finishing in another 5-10 minutes. So okay, this question is the examination of X-ray diffraction data for magnetic steel shows two phases, alpha ferrite BCC, gamma austenite FCC. The integrated intensity of the 110 ferrite line is 25 and the austenite line is, so ferrite is alpha and this gamma is 3, both in arbitrary unit. We don't have to worry about the unit. Calculate the volume percentage of the retained ferrite in steel given R alpha by R gamma is equal to 1.5. Okay, so I'll be putting this, I'll be writing this equation. I alpha, we know that from the direct comparison method, I alpha by I gamma, let's say here two phases are there, alpha and gamma, is equal to R alpha into C alpha divided by R gamma into C gamma. Right, here it is given to us that the integrated intensity of the ferrite line, that means the alpha line is 25, the gamma line is 3. I alpha is 25, I gamma is 3, is equal to R alpha by R gamma. It has been given to us 1.5 into C alpha divided by C gamma. From here we will be getting C alpha by C gamma is equal to 25 divided by 3 into 1.5. So it will be 4.5. This value will be how much? Let me write 25 divided by 4.5. It will be 5.55. Okay. Now, so C alpha is equal to 5.55 of C gamma. Now we know that C alpha plus C gamma, since it is a two-phase system, will be 1. That means C alpha will be 5.55 C gamma plus C gamma. So here C alpha will be 5.55 C gamma. So that value I put it here is equal to 1. That means 6.55 C gamma will be 1. C gamma will be 1 by 6.55, and subsequently you can calculate C alpha as well. Okay, it might be coming somewhere 6.5 means it might be coming somewhere close to 15%. This value will be coming somewhere close to 85%. It should come. Okay. Now there is a multiple answer MCQ. So which of the following statement is or are correct? Microstructural information in quantitative X-ray analysis. Smaller crystallite size in nanocrystalline materials, an inhomogeneous composition in a solid solution, more stacking fault, microstrain and other defects in crystal system, peak broadening. So which of this information are correct? Which information we get when we do the quantitative analysis? Quantitative means all the size effect, all the strain effect, all the composition, what is the phase fraction, what is the volume fraction. Okay, those information I am mentioning. So can anyone answer? Okay, so the answer will be, okay, we'll see statement 1, smaller crystallite size in nanocrystalline materials. Crystallite size, when we talk, that means it is Sierra's equations. So when we do a quantitative analysis, we will get the crystallite size, or the crystallite size is given by B or D, any, it's just a notation difference, but this statement is correct. An inhomogeneous composition of a solid solution, if we are having a different composition, then also we will get this information. How? By direct standard method, or by direct standard, how much volume present in that material, volume fraction is present in that material, we will be getting this statement as well. More stacking fault, microstrain, other defects of the material, it will certainly give the broadening of, it will certainly incorporate broadening in our peak, and finally peak broadening. So all 4 are correct, so the answer will be all of this statement. So in a quantitative analysis, when you do, you get all this information. Okay, qualitative analysis means you are indexing the peaks. So that is what called as qualitative, because you are matching the quality of your peak or the goodness of the fitting that you are doing with your standard sample, which has been done in ideal condition. So that is what, how quality wise you are matching to that standard. So that is qualitative analysis. Quantitative means what information of your material that you are extracting. So that is what known as quantitative analysis. Yes, saying all this thing. So here the Williamson-Hall equation came. What strain is required to cause the total peak broadening as FWHM this much radian, assuming theta 60 degree, lambda 1.5 angstrom, crystallite size is 1350. And hint is also given, Williamson-Hall equation B, I am writing it here again, B is equal to 0.9 lambda divided by T cos theta plus 4E tan theta. So why I told that Williamson-Hall equation is Fw cos theta is equal to K into lambda by D, means my equation I have written D plus 4 into strain, let's say into sine theta, right? I have written like this, but how I am saying that this is the Williamson-Hall equation? If you put this cos theta down, so it will be Fw is equal to K into lambda by D cos theta, right, plus 4 into epsilon into sine theta by cos theta, that will be giving us tan theta. This has been written it here. So this also you can write it like this. So here D or T, both are same. Okay, so yeah, so what does it has given? Lambda it has given to us. I'll just put a different color to the material that has been given. The information, lambda has been given here, right? So it is asking us about this thing, strain. Theta is already given, tan theta, cos theta, these values are given. T is given. T, crystallite size it has given. So crystallite size, this is T, this is B. So B is given, T is given, lambda is given, everything is, yeah. So you just have to put all this information in this equation, and then you have to calculate this terminology. So has anyone calculated? Is anyone having calculator? How much is it coming? If it is not coming exactly, then you can choose the approximate, the closest value also. So since you are we are talking in terms of angstrom, so there might be some amount of here and there plus or minus values will be coming, so you have to round it up. Has anyone calculated? I'll just check the answer. Answer will be, I think, yeah, the B is the answer. Okay, if you calculate, the B will be the answer. Okay, which of the following statement is true? Quantitative analysis applicable for continuous solid solution? Definitely true. Determine the composition of single phase, not amount. Yes. Composition, how much it is present? That is true. Accurate method of determining the chemical composition. If this is true, then this is also true. So the answer is 1, 2, 3. Which one is 1, 2, 3? C. Same quantitative analysis. So just do it. Here, this kind of MCQ might come in your examination, final examination. If size broadening is the only contribution to the peak width, what will be the Williamson-Hall plot looks like? A linear line having zero intercept on the y-axis, vertical, linear, none of this. What will be the answer? Can any one of you answer?
Sir, D, sir.
Which one?
D, sir, none of the above.
Okay, yes, correct. That is the answer. So when Williamson-Hall plot is like this, right? So when only size effect is, so this is the B cos theta, let's say I am writing, and this is sin theta. So when only broadening happening due to size effect, then the curve will be, size effect means it will only be having intercept, it will not be having any slope. So intercept will be coming due to size effect, and the line would be completely horizontal. Here no horizontal is there, So a line having zero intercept on the y-axis, zero intercept on the y-axis. No, it is not like this. Vertical, it will not be vertical. Linear, but it has no linear means it will go like this. It is also not correct. So none of these. Again one quantitative. Okay. So which of the following correct about quantitative analysis by the method of standard addition? Here this is the standard addition. This we know you do it as internal standard as well as external standard. So we do the quantitative analysis by internal standard, external standard. What do you mean by internal and external standard? Let's say I'm talking about in terms of internal standard. That means we don't know how much phase, how much intensity we will get, how much phase fraction we will get by the addition of any random material. So what we do, we take our material, we add some amount of standard material to them, known standard material to our material, then we will be getting some amount of intensity, right? So let's say I alpha is intensity of my material, then I add some amount of standard material, then some intensity changes will be there, then I add to this my material, I add my second material, let's say I beta I add instead of standard standard material, then I will get some other intensity. By comparing the intensity that I got adding standard material with the intensity that adding my second material, I do the calculation and I calculate the intensity between them, and accordingly the volume fraction and the weight fraction between them. So this method, this is the standard method, internal standard method. Also external standard, similar principles are followed. So also, yeah, also this is also known as spiking method or doping method. Why doping method? Because I am doping standard material into my material, or I am doping a second phase material or a third phase material into my already mixture material. That's how I always compare them, compare the intensity. So this is why the peak intensity is first measured of the phase of interest, then again measured intensity after adding a small amount of this phase. Okay. So in this case, so all of 1, 2, 3, you have to remember this thing. This is what internal standard method, what we do. Okay, I think this is the last question, or is there anything? Oh. So the following statement is true or false. The absorption method requires the measurement of intensity from a diffraction peak in the mixture and from a pure standard material. So is it true or false? This is the previous questions that I discussed now. Not exactly the previous question, but yeah, standard method we are following. This is the external standard comparison that we are doing. This is a true statement that we add. First we calculate the intensity, we take some intensity, okay, then we add standard material and then we compare that intensity. So this is a standard. So this is how the intensity, the quantitative analysis of a powder mixture, when we are talking about like this, we do the quantitative analysis. So this is the last question. The following statement is true or false. A perfect defect-free single crystal XRD peak profile shows peaks, diffuse peaks. Whether it's correct or wrong. Can anyone of you answer? Is anyone there or not? Yes. Okay, someone has answered, I think. B. Yeah, that's correct. Diffuse scattering will not be there, because a perfect defect free single crystal means it will be having very high intense peak, and it will be very narrow peak. We will be getting high intense peak as well as narrow peak. There will not be broadening. Why these diffuse peaks are coming? Diffuse peak generally comes due to the poor crystallinity of the material, and if we are talking about a single crystal, then there is no question of poor crystallinity, defect free, no broadening effect, no amount of broadening will be significant also, and a perfect crystal we are talking about, so it will be a false statement. Okay, so yeah, that concludes our classes today. Is there anything? No. So that concludes our classes for today.